Thank you, Webb, for organizing this great workshop, and glad to be back. I got my PhD here, so it's in this room. That feels great. From yesterday and today, we have a lot of talks on different methodologies. That's all the great summaries. So I won't go too much detail into the math, but I want to directly jump into some application of using all those different approaches in quantitative PET and SPECT. So I want to. So cover some denoising, attenuation, correction, and image reconstruction. So starting with denoising for nuclear medicine, we really want to have absolute quantification of the radio tracers. So quantification is really critical. But when you look at different denoising algorithms, so typically when we try different approaches, a common challenge we have is denoised images tend to be over-smoothed and lots of details. But more importantly, we'll lose some quantification. So here for it's low count images, even though the image noise is pretty high, but if you look at SUV mean of a region, because MLEM, reconstruction, OSEM, we still preserve the count, even though there's a fluctuation. If we draw a big enough ROI, the mean quantification, that's still very well preserved. But however, for different deep learning-based approaches like this in the UNet, we're having a lower image noise, but the quantification was really degraded, has underestimation. Comparing to a ground truth. So we really want to see for most of the denoising algorithms how we can restore the quantification accuracy. In the meantime, we can still maintain a low image noise. So one approach we are looking into is to have to integrate the image segmentation into denoising. So that's some of the talks yesterday, how the different priors, different contexts. So what we try to see if we can use a pre-trained segmentation network to separate the physiological and the pathological uptakes to give us a probability map of the lesions. So we feed that lesion probability map into the denoising network so that denoising can be different architectures. In this case, for example, we use a patch-based approach, so we can use, based on this lesion probability map, we can oversample the patches that contains the lesion so that we can preserve the quantification accuracy of the tumors. So here's the examples, 2 patient cases, 1% or 2% low count images, and the second column are the networks we have without those kind of anatomical lesion segmentation additional information. We have the underestimation of the quantification, or having this third column is what we have with the segmentation integrated with the denoising. You can see that we can effectively recover the quantification while still give us a pretty low image noise overall. And here are the segmentation probability map that give us the additional information. So we didn't really have this hard binary segmentation to guide denoising. We try to use a soft way to use a probability to guide this denoising. So what we just talked about is a way that we use denoising to help we use the segmentation to help denoising. Well, we can also think about the way that is it possible for low dose PET, we want to have a segmentation, but also we want denoising. Is it possible we can have the both tasks helping each other? We can use denoised images to help better segmentation, and also the segmentation helps the denoising. So in this case, we have this approach called anatomically and metabolically informed diffusion model for unified denoising and segmentation. So the approaches we have is we go through each component. So on top, we have the denoiser, and the left component, we have a conditional diffusion model. And once we have this diffusion model have a denoised images, this denoised images come to the second component here is the segmenter. So this is segmentation-based approaches. Here we have this low count images. After this denoiser, we give us a low noise PET images and give us a segmentation. And we have both lesion segmentation and also organ segmentation from these denoised PET images, and these segmentations come back to this denoiser to give us, similar to what we just discussed, have using the lesion to help the quantification, but also have the organ to give us a more like an organ-specific denoiser. So that kind of this denoiser component is a denoiser and a segmenter working with each other to give us a simultaneous uniform segmentation and the denoising. And when we go to the inference case, well, since it says maybe auto battery or so, just use this one. Yeah, I can see my mouse. So for inference, we don't need segmentation. We directly take the low count images and the random noise and feed it into this network. So it will give us both the noise image and also both lesion and organ segmentation altogether. So here are some examples of evaluation of the denoising. So here is the input. This is the 5% Siemens MCT scanner data. Here are several different approaches. The second approach is what we just described, using segmentation to help denoising, but not the other way around. But here is the AM, this diff approach. You can see that we can have pretty good quantification of the tumors, but also give us overall image denoising. And also the quantification numbers, also this gives us the lowest mean square error on the whole image. And when we look at the evaluation of the segmentation of the lesions, here is from very low, with high noise, low count images, the segmentation will be unreliable. And here we have the segmentation based on the reference based on high count images. And you can see different segmentation approaches directly applied to these noisy low count PET images give us pretty, some of give us better, some of worse, but overall there's a lot of errors. While this approach gives us, our proposed approach have a segmentation denoising together, give us a pretty consistent lesion segmentation comparing to the reference, particularly for some smaller ones here. And also looking at the organ segmentation, so here is the denoised image. If different applications, different approaches for organ segmentation give the reasonable results, and this one, our proposed approach gives us the best, most consistent segmentation comparing to our organ label. So these organ labels were based on CT images. While our network generated this organ, we don't have CT. We directly get the organ segmentation purely from PET without CT, but also you can see some of the ribs kind of show up with our proposed approach, showing the effectiveness of this approach. And also dice coefficient give us the highest dice coefficient comparing to other approaches. So here is an example of, in the diffusion model, we have a segmentation and denoising together to kind of give us a simultaneous denoising, organ, and lesion segmentation, all three tasks. So take a step back to look at the diffusion model we are using for our PET images. So PET, we have this whole body PET, lots of larger volumes. 3D diffusion is really not realistic for our data set. And we try different approaches, but first of all, if we go to just have the memory kind of efficient 2D slices for diffusion, we can see all those kind of the inconsistency across different axial slices. If we just loop through all the slices, you can see just all the 2D approaches is just really not consistent across the slices. And another challenge of the diffusion model, if we're just using 2D diffusion applied on 3D PET, is we're really having a quantification bias. So this is something for nuclear medicine we just mentioned. We really want the absolute quantification of the tracer uptake. But you can see here the brain uptake is dramatically underestimated using these approaches. So that's something definitely is a red flag. And also, if you look at some particular images like the myocardium here, you can see even though diffusion model gives us visually appealing images, the myocardium, but you can comparing to the full dose, it's just not the same. It's just wrong in terms of myocardium. Seems that there is a perfusion defect here, but actually that's not there. It's not there in the full count images. So this is an example, probably is an example of a hallucination that really will try to address that using the diffusion models. So we tried different approaches to try to address those challenges. So one is for the 2D slices, instead of going from 2D to 2D, we're trying to see if we can use neighboring slices. Still we generate every 2D slices, but the input of those 2D slices are not just a single 2D, but neighboring slices. So we find out memory permitting kind of 9 slices. We don't see that tumor, but if we increase the slices into like 31, using 31 slices to generate each single 2D slices, then we can get a pretty good axial consistency, but also those tumors, some of the hotspots started showing up. And also to address the inconsistency across different slices, now we have neighboring slices, but also start Gaussian noise, concatenate together to get the central slice. However, because the inconsistency of the slices, we're trying to see, can we start the same Gaussian instead of different random Gaussian? So if we fix a starting Gaussian, then we can have less changes in the input and have more consistent output across the slices. So here, just what we just showed here previously, if we use a different Gaussian, random Gaussian, to have a different 2D slices, we have this inconsistency. If we fix them together, if you look at the last kind of going through that, we still a little bit of inconsistency, but it will give us much better results compared to the previous version. And also, the last step is when we have a fixed the starting Gaussian noise, but also sometimes we see the Gaussian's dependent artifact. So we try to use the starting with the multiple Gaussians to compensate that. So here are some example. If we fix the Gaussian, so we no longer see the axial slice inconsistency, but we're seeing some vertical slice artifact by just using just one Gaussian starting point. So now we can see if we don't fix that with 2 Gaussians, then we have a horizontal artifact. So we're trying to see if we can use 2 Gaussians. If, of course, the more the better, but a fixed Gaussian starting point, now we can, having them averaged together, gives the better results. We're eliminating both this vertical and horizontal artifacts. So with all this together, the last missing piece is the quantification, which is show that the brain is largely underestimated, what we can do with that. So we're trying to see, well, if we can have even though the UNet-based other convolutional network give us a denoised image, a little bit more blurred, but the tracer concentration is really preserved in that cases. So we try to generate a UNet-based denoising prior first, and for the inference, now we start with that UNet instead of, so that can really maintain the quantification accuracy. You can see here, the no prior, this brain is largely underestimated, but with the prior from the UNet, we maintain the quantification accuracy, and after all these diffusion models, we have also better resolution, so with the quantification maintained. So now we're kind of putting all those together. So here is an example of 1% counts, pretty noisy PET images. CNN-based approaches give us reasonable, but still have some artifacts here. And here are 3 different diffusion models in the previous publications, but all have some limitation in the axial slice, and also they all have the hallucination, the kind of the inaccurate reconstruction of a myocardial uptake. Well, our proposed approach, you can see that we can maintain the quantification, also the brain, but also the myocardial uptake. We have a pretty consistent tracer uptake comparing to the ground truth. So moving forward, not only we want to have visually appealing images, we want the physicians to give us input if these images are really what they like. So here we have 3 different center data sets from Yale data set, is Siemens MCT, and Shanghai region is a United Imaging 2-meter long Explorer, and Bern from Switzerland, they have the data from Siemens Quadra. That's a 1-meter long total body scanner. Then we have 3 different readers. We present, this is a kind of observer study. We present 5 different images and with a random order. So we just want the physicians each time to give us a ranking among the 5 images, which one is the first, which one is the last, based on overall image quality. And the best one is the ranking equals 1, the lower the better. So here at the starting point, we have given them a full count images. That's where they have typically 3. If we give low count, 10% or 20% noisy images, they typically give us a number of 4 or 5. While looking at using after the diffusion model, process the 20 and 50% count level, you can see that the numbers are much lower, so indicating that they rank those images even higher than the 100% full count images, but without diffusion model. So showing that it's feasible, it's possible that the physicians prefer the low count images with denoising using diffusion models. And also, but that doesn't tell us the detectability of the lesions. So in this case, we use a Monte Carlo simulation to generate lesions in the sinogram raw data space, and we insert them into the raw data in the PET image and reconstruct again, so that we can know the location we can have an absolute lesion, the cases that we know that the lesion absent, but also with true lesion present cases, we can run observer studies. So this is the case we use a non-pre-whitening matched filter. We can see different sizes of the tumors. Interestingly, for very small 4 to 6 millimeter tumors, with and without diffusion model, the detectability did not really change. But for the 8 millimeter, the largest one, diffusion model does give us higher index for the non-pre-whitening matched filter. So right now, this is an ongoing study. We're also moving on to channelized whole titling observer, but also we're using not only simulation from Monte Carlo, but also spheres acquired from the scanner, and we merge those raw data of the sphere and also the lesion absent patient together. Then we're performing, moving forward to potential human observer studies. And for all the first models, we also apply to cardiac SPECT. We have LISMO data. We can repeat them different count levels. But for SPECT, for this data set, it's smaller. We have the projection data, and we can include DPS into it. And also the size of the projection data is more manageable. So with DPS and also diffusion model, we described in the PET implementation, you can see for even 1% of the counts, extremely noisy images, we can still get a very reasonable reconstruction of the myocardium. Well, this is not black hole as we talked yesterday, but this is the myocardium of the perfusion SPECT images. But you can see, but the polar map is give us the more, that's more the physician looking at the polar map for diagnosis. You can see once we reach about, if it's 5%, 10%, even though the images are visually appealing, but the polar map is just not the same as a 100% label. And we really need to have, once we have reached 20 to 50%, we get a pretty consistent polar map for using the diffusion models. And for we discussed yesterday for black hole, we don't have a gold standard, but here for cardiac SPECT, we do have a gold standard. And we have an invasive CAS that really we know those are the defects, are true defects, and give us higher resolution and contrast with diffusion model for those locations that corresponding to the invasive CAS. So moving forward to a different application, similar to cardiac, rubidium is the most widely used perfusion flow tracer in cardiac studies because it doesn't need a cyclotron. It's just a small generator can work for all different hospitals. But the problem of this tracer is it has a very high positron energy, so that it travels a lot longer before annihilate, get the 511 keV. So the positron range is really high. So comparing to F18 tracer, you can see the rubidium, we can have a, depending how you categorize that, probably a 3 to 5 millimeter resolution loss just due to the positron range. So without doing anything, we have already lost that amount of resolution. So, and also this tracer has only 75-second half-life, so the image noise is really high because of decay. It's great for patient radiation dose because of short half-life, but the image quality is really poor. So we want to tackle both positron range and the noise for rubidium cardiac PET. We try to see how we can combine them together. So in this case, because rubidium had a 75-second half-life, decayed so fast, it's really hard to get a very high count training label for this application. So we try to use a self-supervised learning, randomly crop the voxels through a noise to void based type of approach. Also positron range correction on the other side of the picture, we use a Monte Carlo simulation based positron range kernels, and we have this denoising, the left denoising network and the positron range correction network trained together. Kind of see, we can try to have this simultaneous correction. So here is an application of the positron range part only for a delayed cardiac SPECT images. You can see the resolution improved and the papillary muscle shows up, and this papillary muscle has been confirmed by the contrast CT. Indeed, this is not a hallucination feature. This is a real feature that's been confirmed by the contrast enhanced CT. For rubidium, we always use dynamic to calculate the myocardial blood flow. So here is a dynamic image from a tracer injection, goes to RV, LV, and myocardium. And you can see that for denoised frames, we can reduce the noise, while for positron range correction, in combination with denoising, we can have a better resolution. When we fit all the voxels, vox by voxels through a tracer kinetic model for 1T model to get a K1, to get a myocardial blood flow, then we can generate a myocardial blood flow map, voxel by voxel. So you can see without any corrections, this noise, this K1 map is extremely noisy. And For denoising, we give us a reduced noise, but with partial volume correction, it improve the resolution. The bottom map is through this kinetic modeling, we also fit VB term, which is a blood volume term. So if the tracer, so it is basically you can see the in the blood pool is 100% blood, that's equal, number should be equal to 1. But without the positron range correction, there is a blurring in the septal wall between LV and RV, and we can correct that with positron range correction, and we validated it with O-fitting water. This is a tracer with very low positron range, but to generate that, we really need a cyclotron, 2 minutes half-life. We need a cyclotron next to the scanner, and fortunately, we have that at Yale, and we have the same patient going to O-fitting water and to rubidium to validate. You can see the rubidium, the O-fitting water has separation between LV and RV, which can be achieved a similar separation for rubidium with positron range correction as a validation. So moving forward to attenuation correction, we have so both PET and SPECT, we can now generate synthetic CT-based attenuation map from emission data. For PET in particular, because we have time of flight information, we can use time of flight at maximum likelihood reconstruction for activity and attenuation together. So that gives us an activity map and also the attenuation map. But it's a very low radiation dose. In that case, both maps are highly noisy. So the attenuation map, because it's generated from the PET data, is the noise in the attenuation map will subsequently propagate into through attenuation correction into PET image. So we can always use a CT-based attenuation map as a label, train a network, right? The input is both MLAA output from activity and attenuation. Predict attenuation map using CT-based attenuation map as a label for training. But you can see that in this case, we're losing the resolution because of this map based on the PET images with the worse resolution. So some of the features, some of the fine details from CT can never just be recovered, likely due to the network, we have downsampling, upsampling, we have the resolution loss through this process. So to compensate that, we propose approach. It's called over and under representation network. So the bottom here is a more conventional. We have a UNet type based. We have downsampling first and upsampling. But also in the top one, we have an oversampling network. So it's through an oversampling and a downsampling. So I have both networks and come back to the center. The central path is we combine the output from both undersample and upsample network together, and also each step, the features from each step of the under and oversampling are fed into the central path. So in that case, we can have a final mu map attenuation, and for those all three passes, we have three losses together, training all those together for attenuation map generation. So here you can see the conventional UNet give us attenuation map. Here is with losing some of the features. This over and under sampling approach will give us some of the ribs, some features are showing up. But if we compare with the ground truth from CT-based attenuation map, there are still some feature loss. So we try to fill the remaining gap. And also there's another case, right? You can see that we're doing better with this over under sampling, but still there's a feature loss. So we try to, based on that, we have another implementation. We develop a population prior generation machine, which is based on about 2,000 CT images. So the output from the previous network will be fed into this generation machine to see among all those 2,000 CT images, which one best fit into the output of the previous network. Then we use that for non-rigid registration to the output. Then we generate a new attenuation map. Then we feed this new attenuation map in addition to the maximum likelihood reconstruction of mu and lambda. Now we have three output into the next next iteration of this network. So we're going iteratively. So at the end, we can generate, so this is the previous detail level from over under sampling. Now with this, with population-based new prior machine generation incorporated, now you can see all the fine details are pretty consistent with the ground truth from the CT-based attenuation map for attenuation correction. So here's another case. You can see that some of the ribs, some of the lung in those features have been recovered using this approach. And feeding using this new attenuation map for attenuation correction, you can see now the bias is pretty minimum comparing to either UNet-based approach or even MLA-based approach. Because this is only 2.5% counts or 10% counts, the noise is really high. Those approaches are really kind of not, really give us a higher bias, which can be compensated by our proposed approach. Okay, so lastly, I want a few slides on SPECT reconstruction. So for SPECT, particularly in the dedicated cardiac scan, SPECT, these are the scanners we have at Yale with 19 projection angles from the CDT solid state detectors. There's no rotation. So 19 projections give us a reconstruction like this. But if we rotate it, we can have more projection angles for reconstruction, give us better images in the myocardium. But however, it's not really feasible or convenient to do it in the clinical practice. So we train the network combining with simulation, large animal data, and limited human data, all combined together to train the network. We have several different versions. This one is a transformer-based approach. So you can see the one angle reconstruction, 19 projections versus 76 projection, equivalent through deep learning reconstruction. We have a higher resolution, contrast, and also the defect hasn't shown up here. And also with a full 4-angle, that is the gold standard or the reference we can have. And we have a resonance stress scan showing, in this case, we have a reversible defect for this patient, which had been confirmed by invasive CAS. So this one, I just want to show this one as a stepping stone for the last few slides for this application. So we have talked about denoising, attenuation correction, limited angle reconstruction for dedicated cardiac SPECT. If we combine all of them together, there's one unique application is this. So this scanner, as it's mentioned, has 19 projection angles for reconstruction for cardiac, while scanner from GE. And now CDT detectors, solid state, is very expensive. And right now they have a new version, which is they call it cost effective, which is basically a cheaper version. They get rid of the top and the bottom 10 detectors, only leaving the 9 detector in the center. In that case, cost is cheaper, but we have a fewer number of accounts and also more limited angle reconstruction, sparse view reconstruction problems. So we develop a network. We try to see how we can address this scanner. Also, this scanner does not have CT, so they want to put it in the small footprint in the cardiologist's office without referring patients to the radiology department, large scanners. So in this case, we have networks. It's a dual domain. So on top, we have projection-based projection domain network. We try to take the low dose, for example, 10% low radiation dose, 9 detector projection data to convert that into a full dose 19 detector equivalent projection data. And on the bottom is an image domain network. Take the images and want to generate a deep learning based synthetic attenuation map for attenuation correction, equivalent to CT-based attenuation map. So the network on the top is a 2-stage progressive network in each component. The first downsampling, upsampling for the sparse view recovery of the angle, but also there's a non-downsampling, upsampling network for denoising. And on the bottom is we have a boundary aware network, mainly because for this dedicated scanner, the reconstruction field of view is only 19 centimeter diameter. Smaller field of view only covers heart, but that does not cover the whole body. So it's really hard to get a whole body attenuation map from this smaller field of view reconstruction. So we need additional boundary information. So here are the examples. You can see that if we look at this green box, this particular projection angle, ground truth, high counts, 100% counts, this is 10% of counts. Noisy images, we have a different denoising approach with other things, different networks, but at the end, this dual domain gives us the lowest bias and recovers the high, the low noise projection angle. And the next one is I'm most exciting about is if you look at this red box, this particular projection angle, for 9-pinhole scanner system, this projection angle does not exist at all. So even though the ground truth is here, but our input is black, there's nothing here. So, but still within this our dual domain network, we can recover a reasonably well recovered projection angle even from nothing. So now we can have this recovered projection angle effectively for 19 projection angle from this 9 projection angle. Here, similarly for attenuation map, some of the networks have some little bit of artifacts here and there in the boundary in particular, but because we have a boundary constraint in our network for image domain, the bottom one, so we can have a pretty nice attenuation map, similar, pretty consistent with the CT-based attenuation map. All combined together, we're turning a very cost-effective 9-pinhole scanner without CT to a hybrid SPECT CT-based high-end scanner with attenuation correction, and the correlation is pretty nice, voxel by voxel. So yeah, so that's the summary. We talk about some denoising, attenuation correction, image reconstruction in both PET and SPECT, and the quantification is probably a major concern in our applications, applying all those different networks. I really appreciate the funding number of funding agency, mainly from NIH, of group members. Well, thanks for attention. But before that, I wanted just to have one announcement, advertisement. So if the IEEE TRPMS had a special issue on generative AI on radiation imaging, Kwang, Gong, and Webb, and myself are guest editors. So with the June 30th submission deadline. So that's something, if some of the work we're all doing, we can consider that. Thank you for your attention.
Great. So we're open for questions. We have several online questions. This comes from Sichi Lee. Nice presentation. For denoising and segmentation, does the segmentation result, that is the shape, affect the quantification of the denoised image? And what if the lesion is small and non-avid in low-count PET?
Mm-hmm. Right. So it's a good question. So right now if the segmentation network give us a segmentation of the lesion, we'll take that into consideration. For example, when we sample our different patches, if it contains the segmented lesion, we'll give a higher weight based on the probability. So if whatever reason the segmentation did not work very well, miss that lesion, we just don't give a higher weight. So I would say that probably we're not losing anything, but if we have that lesion information or appear in the segmentation, then it will give us a higher weight.
Hi, very interesting talk. You covered so much, but one specific thing that I was curious about was, there was a ranking of preference by radiologists of methods, and then there was a task-based assessment using a non-pre-widening observer. And from what I thought I saw, the radiologists liked it better, but the observer said there was no difference. I wonder if you could elaborate a little bit about the difference between radiologists overall liking it and task performance.
Yeah. So this is first of all, it's two different data sets actually. So it's hard to compare them together. So just in general, when we have if other physicians or human observer to look at whole image quality, the preferences. From the interactions with them when they're going through this email, sometimes they're more like a liver noise level. It is something they're really looking to for their visual quality evaluation. That's something they look first, and some of the fine features. That's where they look at when they look at the overall image quality. Well, the observer study, of course, that's a kind of we give them the location or the searching, other things. That's a lesion detectability. That's at this point, where this is still ongoing work, we don't have something to compare both because they're not same data set at this point. But I think it's hopefully, yeah, it's good. It's similar to a kind of earlier talk from Grace. That some of the evaluations, and if we can have a comparison, different metrics, a human observer, a massive observer, different tasks, and looking at all kind of bigger picture, that would be great.
Thank you.
Great. Another online question from Bruno Deman. Great work. Going back to the example of the hallucinated perfusion defect, can you determine the minimum dose level needed to guarantee that critical image features like perfusion defects are contributed by the data and not hallucinated by the prior? For example, 1% dose may be too low, 2% may be more trustworthy.
Right, exactly. So that's a great question. That's exactly what we're doing right now. One of the paper in the revision, we put that in the revision. So hallucination, if we can have some way to quantify that hallucination, Qianzheng has some work and Mark has some work on that. If we can determine that and some matrix, some quantification indexes, And it's not only being used to evaluate different approaches, but it could help us determine, like say, some of the noise level is too low, regardless of what we do. It's just not feasible to give us the best the image without hallucination. It could be like 20-30% of the counts or something. That could be that could help us determine the threshold. But I think we discussed earlier, it's a hallucination identification evaluation kind of is still an open field right now. We put some thoughts as Society of Nuclear Medicine probably we're going to put in a kind of position, a paper, something like to give us some thoughts. But I think that as a field here, that's something, the next step, we really have to probably kind of give it more thoughts and develop some guidelines and ourselves.
Great. And perhaps one last quick question from Jyoti Chand. Are the denoiser and segmentation networks trained jointly?
Right. So the first work I showed, that segmentation was trained separately. Train segmentation first, and then you feed that segmentation results into denoising. The second part I showed that one is jointly trained, the simultaneous denoising and the segmentation.
Thank you so much. Let's give him one more round of applause.